Thank you so much. And what a lovely intro. Thanks, Paul. Yeah, as Paul said, I'm really happy for you guys to jump in with questions if you have them. Please feel free to interrupt me. It's all good, especially if I say something and you're not quite sure what I'm saying. So, kia ora, as we say here in New Zealand. And yeah, I'm also in Auckland, so today the weather is actually quite lovely. It's stopped raining just for a little bit, which is amazing. Right, so what are we going to discuss today? So we're going to talk a little bit about what actually machine learning is. And then we're going to cover some things that are really important, but are, I suppose in some respects, not actually machine learning proper, but if you don't do them, your machine learning is not going to give you the kind of results that you want. So we're going to talk about descriptive stats and correlation coefficients, what they are, why they're important, and why you need to make sure that you've got a handle on them. We'll talk about understanding your data with visualizations, and this becomes particularly important if you're talking to other users about data. So perhaps you're talking to some business users. I found in my experience, it's much better to share pictures rather than tables of numbers. We'll talk about pre-processing and transforming data, what it is, why it's important, the different kinds of things that you might want to do from a transformation point of view. Then we'll get into the machine learning stuff. So we'll talk about supervised versus unsupervised machine learning. I'll touch on the probably the most popular linear and non-linear algorithms. And then we'll discuss some performance metrics, and we'll discuss comparing algorithms. So basically, how do you know your model is working and which model is better? And there are a couple of caveats around all of that, which we'll get into as we go there. Right, so what is machine learning? Machine learning, it's a type of artificial intelligence, and basically it allows the computer system to learn and improve from experience, and it doesn't need to be explicitly programmed. So essentially it uses a number of constraints and mathematics, lots and lots of maths, to work out predictions. It takes this data and it makes predictions or decisions, and it does this without being explicitly told what to do. So you don't have to tell it which variable is important. It works out which variable is important. You don't have to tell it, you know, at what point to split the variable, because that's what it does to work out. Algorithms are used to identify patterns and relationships within data. And they're typically really good at doing this, better than humans are, or can be better than humans are. And then as they have more and more data, so they learn more about the patterns and which ones are really true patterns versus which ones are just outliers that maybe looked quite good initially. We use machine learning in all sorts of applications. So as Paul mentioned, we use machine learning in credit risk and in finance, but it's also used in things like speech recognition, image recognition, natural language processing. And basically what we're trying to do is enable the machine to do the learning. And the goal is usually to predict with the greatest level of accuracy. But as I said earlier, before we even get to the super exciting stuff, we need to get to some of the less exciting stuff that's really important. So let's look at some descriptive statistics and correlation coefficients. So numeric data, when we talk about descriptive statistics, typically you can so whether you're looking at SAS, whether you're looking at Python, most of these programs have an ability to run some sort of a function, and that gives you your key descriptive stats. So your mean, your median, typically your 25th and your 75th percentiles, minimum, maximum, standard deviations, skewness, that kind of thing. When we talk about classification data, then we want to count how many classes do we have and how are those classes distributed. So for example, in fraud, you could consider, is someone fraudulent, yes or no, and you could look at the distribution of those two classes. And typically with those sort of models, you see really unbalanced data. Otherwise, you could look at, say, male versus female, and that is where you would expect it to be typically far more balanced. So you'd expect roughly 50% of your data to be male and 50% of your data to be female, unless you were working in a field that was very dominated by one gender or another. When we start looking at correlations between two variables, what we're looking for is correlation is not causation. Let me just make that really, really, really clear. So what we want is we want to see how variable A and variable B are related to one another. Does one go up and the other one go up? Or if one goes up, does the other one go down? Do they vary in sync or not? And one of these, the reason it's really important to understand is because in a lot of models, you don't want to be putting or using variables that are too strongly correlated with one another. It causes all sorts of problems, primarily overfitting. -1 to +1, full negative or full positive correlation. 0, no correlation at all. So when you're looking at your variables and you're looking at the correlations between them, anything greater than a 0.8, I consider to be a pretty strong correlation. Anything less than a 0.2, fairly weak correlation. Anything in between, be a little bit cautious about. So typically, if you've got variables that are really strongly correlated, you don't want to include all those variables in your model. You're likely to create an overfitted model. There are ways around that, and we can discuss that a little bit later. Where your R squared is weak, so very low correlation, fantastic. That means that the different variables are giving you more information. And therefore, you can add variables that are weakly correlated together because you're getting more and more information. By adding various variables that are strongly correlated, you're not really getting much more information. And the reason this is really, really important is to understand this is because it has an impact on how people see you. If you put too many variables that are similarly correlated, someone might say, well, why use this one and that one? Which one's better? Which one's, what is the value? And that's where picking the strongest one, the one that's most predictive, is generally the better idea. Let's talk a little bit about visualizing your data. So once you've done all this work around understanding the correlations, Caroline? Yes.
Sorry. There was a question that's just come up. In the previous slide, it was asked, can you give some real life scenarios of some of these?
Sure. Actually, let me just bring this chat up and see if I can. Real life scenarios for some of these. When you say scenarios, are you talking about correlations or classification? Sorry, I just need to know which the.
I think the correlations. Just
okay.
Just trying to imagine how it would happen in real life.
Right. So I'll talk about my world, which I'm most familiar with. Let's say someone has missed a payment. So they've got a loan account and they've missed a payment and they're now in arrears. Someone who has one payment in arrears might be very closely correlated. So the data might be very closely correlated with people who are, say, 2 payments in arrears in terms of, are they likely to become more delinquent? Because in all of these things, what you're trying to understand is how these variables may be related to your predictive variable. So if 2 variables behave very similarly, so when the one always goes up, the other one always goes up, then what you find is that by including either one of those variables, you start getting your model. So to use a slightly silly example, when the temperature goes up, people drink more water because as the temperature goes up, so people become hotter, so they want to therefore drink more things. So depending on what you're trying to do, you could either say, how many glasses of water is everyone drinking, or what's the temperature? And those two things are correlated. Does that help?
That makes sense. Thank you very much.
Cool. You're very welcome. So let's jump into, oh, sorry, Carolyn, for a high R square, can we infer that it's more of a cause? No. Abhishek, thanks for the question. So really important to distinguish between causation and correlation. All your high R squared means is that they're really, really strongly correlated. So that means that they move very closely in sync together. As the one goes up, the other one goes up. As one goes down, the other one goes down. It does not mean that the one causes the other. You need to do a whole bunch of other tests to try and work out causation. But absolutely critical that you don't confuse correlation with causation. There's a wonderful website somewhere, which I must try and find, which talks about spurious correlations. And there are the most bizarre spurious correlations that they talk about, where things are going up and they look like they're in sync, but they are absolutely just random acts of stuff. You can't infer causation at all.
Thank you.
So hopefully that helps a little bit. A lot of people are tempted to, but yeah, I would definitely avoid that.
Thanks for that. Yeah.
Sure. Right. So if we jump into some of the visualizations, why do we want to do visualization and what's the benefit? So here I've just put up a couple of visualizations, a couple of charts, a histogram, and a box and whisker plot. So a histogram allows you to see the variables distribution. Now, some people I know have spent years and years and years looking at data tables, and they can take sort of like your standard max, mean, min, median, and look at that outlay in terms of tabular format. And in their head, they picture a graph that looks very much like this. Most of us don't. Most of us need a pretty little picture to help us understand the shape of the data. And the reason we want to understand the shape of the data is we want to know whether it's roughly normally distributed, or is it very skewed one way or the other? Do we have strong outliers? And the reason all this is important is because it talks to what kind of transformations might we want to do. A little bit later on, we'll talk about these transformations. And the reasons transformations become really important is because if you have data with strong outliers, then using some of the linear techniques might not be appropriate, because linear techniques assume that everything is roughly normally distributed. So it's a really good idea to get a fairly good grip on the shape of your data. Is it normally distributed? Is it skewed? So an example of skewness, income. So if you look at a country's income distribution over the whole population, some countries, very few countries, in fact, have anything approaching a normal distribution. Most countries have some sort of tail towards the top end, where people with really high incomes represent a very, very small proportion of the population. And everyone's clustered around somewhere slightly lower down. So you see quite a strong skewness. So instead of using income in its raw format, it might be better to do some sort of a transformation on income so that you don't have these outliers that could be pulling your model in weird and wonderful directions. Box and whisker plots also share something, tell you a very similar story. You can see where the median is. You can see the upper 25th and 75th percentiles. You can see your whiskers. You can see outliers. Outliers are important because you may choose to look at outliers and go, are we going to remove outliers from our data? And depending on what you're doing, that may or may not be appropriate. Unfortunately, I can't say to you, there's a beautiful one size fits all, and if you do the same thing every time, it'll be perfect and magic will happen. Doesn't work like that. And that's where a lot of the skill and the experience comes in. So yeah, that's some of the stories on box and whiskers. It allows you to see where your outliers are, and then you can make some decisions around doing that. Whereas in your other visualizations, you might not notice that you do have outliers. This is known as a scatter plot matrix, and it's quite cool to look at. So what you see down this, and I don't know that you can see, hang on, do I have a pointy thing? I don't know, I have a pointy thing. Spotlight. Let's try a mouse. Don't know if you can see my mouse.
Yep, we can see it.
Oh, awesome. Fantastic.
Well,
there, so, so on this diagonal, you can see the histograms. And what that tells you, oh, no, that's not what we wanted to do at all. Let me take the mouse away. Let me try and do a... Oh, well, sorry. I'll stop playing with the screen. My apologies.
On the left-hand side of your PowerPoint at the bottom, there should be one of those items where you can actually get a pointer.
Ah, you're so clever. Laser pointer. There we go. Oh, you're a rock star. Thank you. Cool. So over here, you can see the histograms. And what this shows you is how this data is distributed. So you can see this variable at the end. Well, you might not be able to see that, it's quite small, entitled class. They're just two variables. You're either a 0 or you're a 1. Whereas this one, age, has a distribution, mostly younger people, and then tailing off towards the upper end. And these are just various variables in the data set that I was using, and you can see how the data is distributed. The other thing that this shows you is the scatter plot. So how this variable is correlated with that variable and how they scatter together. So you can see some of them are quite spread out. Some of them are clustered in a bit of a clump. Some of them have some sort of like correlation. So as this, they go along. So this gives you a little bit of insight into what might be happening with the data. That one, there seems to be quite a strong trend in that direction. So all of these things, this pair has definitely got some sort of a correlation going on here. So you can see how these variables are distributed. So this is quite a useful matrix to understand how your data is working, especially when you want to see where the data is paired with other data. Right, now let's jump into talking about pre-processing and transforming data. So there are several key methods that we typically use. One of them is called rescaling data. And this is often talked to as normalizing data. And basically what you're doing is you're taking all that data and you're transforming it so that the maximum value is 1 and the minimum is 0. And this can be very, very useful in quite a few of your techniques, including gradient descent, regression, k-nearest neighbors, which is a clustering technique, and deep learning. And sometimes you have to play around with it. This one can be very, very helpful with some of these techniques, especially if you're getting weak models. Then we can talk about standardizing data. And again, it takes a data set or a variable that has a normal distribution, and it transforms it into a standard normal distribution. And this is really, really helpful when you're using linear techniques. So a linear technique would be linear regression, logistic regression, linear discriminant analysis, which is kind of like logistic regression, but for multiple classes. So helpful for that, because one of the key caveats when it comes to linear models is that your data is normally distributed. The other thing you can do is binarize data. So everything goes to a 0 or a 1. And there are a couple of different ways that we can do this. You can, if you have a continuous variable, you can set a threshold. So everything that's greater than 0.8 is set to 1, and everything that's less 0.8 is set to 0, for example. You can also use it if you're wanting to do something and you're looking at days of the week. Which day of the week is the best time to, I don't know, make a lunch booking? Or when is it quietest at the gym? That type of thing. And you're wanting to know a day of the week or a particular hour of the day. What you can do is you can say a Sunday is equal to 1 and all other days are equal to a 0. And then you're just testing for a Sunday. So a useful technique. And again, not a complete one size fits all, but useful to know about this and how you might use it. I just want to switch my little laser pointer off. There we go. Jumping beyond the likes of the various techniques to rescale or transform data, let's chat about supervised versus unsupervised learning. So supervised machine learning is the thing that is used most of the time. And it's when we have a predicted variable. So we know what the outcome is. This is typically used in your training and validation data sets. where you go, well, we've got a whole lot of predictive variables, and then we've got this one target variable or dependent variable. It's dependent on all the other variables. And what we're doing is we're saying, right, let's take all these other variables and see whether we can predict this target. Typically, you either do classification or you do regression. Classification, are you trying to predict something as good or bad, spend or no spend, on a Sunday, not on a Sunday. It is sunny or it isn't sunny. It is raining or it isn't raining. Whereas when you're predicting something around regression, then we're predicting some sort of continuous value. So how old is this person? How much do they weigh? What is their income likely to be? How much is the house value likely to be? So those are the kinds of things where we know the outcome for our training data set. We can then use that, and it's called supervised because basically we have something to learn. The model can learn against it. Then the other one that's often used is unsupervised machine learning. And this is where we don't, funnily enough, have a target variable. And what we're trying to do here is get some sort of an understanding of the underlying structure of the data. So we don't necessarily know anything about it. We don't know what outcomes are coming, but we're wanting to learn something about the structure of the data so that we can try and group data points together. The big one is clustering. So how do you know, if you've got a whole bunch of people and you're trying to do some segmentation analysis on a customer database, you would look at all the variables that you've got around your customers and you'd try and group them into different clumps to see who is most similar. And then there's obviously association, which is something is associated with something and something else is associated with something. So it's trying to work out how different things might be associated or not associated. And what you're trying to do with any of these algorithms is you're trying to make the groups most similar. So it's quite a difficult, concept. You're trying to say everyone who's super similar, let's put them together, and everyone who's different from everyone in this group, we're going to put them somewhere else. And then we're going to move these groups around until we've got some fairly stable groups. And that's essentially what we're trying to do in that space. There we go. Then we get on some sort of linear algorithms. And I'm whizzing through a whole bunch of the basics, but hopefully this is making sense. Linear regression has been around for yonks. It's a very popular technique. And we use it for predictive analysis, where we're trying to establish a relationship between the dependent and the independent variables. So basically what we're saying is how do we, knowing something about someone, how do we make that, draw a straight line through it? Effectively, all linear algorithms are trying to draw a straight line as opposed to anything else. It can be represented graphically. Basically, you're putting a straight line through the data to try and get some sort of a best fit. And what you're trying to do is minimize the differences between the actual output variables and the predicted variables. So use the nifty little laser pointer. If this line here is the predicted, what you're trying to do is make sure that all these green dots are, if you take the orthogonal, are as close to this line as possible. So if I drew a line like that, you would have a bigger gap between all these green dots when you start adding up all those errors. So what you're trying to do intuitively, it becomes quite easy. You go, oh, let's see if I can draw a straight line through there. Right, there we go. And that represents the best fit. And that's what we're trying to predict. What's the best fit? It's worth pointing out that linear algorithms are not always the best algorithms to use, but they certainly can be very effective. Key things here, the equation takes a straight line form, so y equals mx plus b, where b is your intercept and m is your gradient. And it's your machine learning algorithm that is used to calculate the slope and the intercept. Logistic regression is similar to linear regression. It's also based on a line. But what you're really trying to do is you're separating for binary. So you're wanting a sigmoid curve. So what you're doing is you're building a relationship between the independent variables or all the features and your target variable or your dependent variable. And in the case of logistic regression, you're always dealing with a binary. So it's 0, 1. And your 0, 1 can be defined as anything you like. It is Sunday or it isn't Sunday or whatever it is. So what we're trying to do is we're trying to take all the information that we've got and determine whether the likelihood is going to be a 0 or a 1. Is this thing going to be good or bad? Is it going to be black or white? And that's what the algorithm underneath tries to do. It takes all this data and tries to split it into these two different things. And it's the probability that it predicts, and that probability is split over the threshold. So the sigmoid curve, it tends toward 0 and it tends toward 1. And the reason that you often use, well, that you use logistic regression and not linear regression when you're predicting a binary is because a linear value, by definition, because it's y equals mx plus c, can go greater than or less than 0 and 1. And that doesn't really make sense. Right. So then we get into some of the nonlinear algorithms, and these are quite cool. So CART, which is classification and regression trees. It is a decision tree based algorithm. It's supervised learning, so you know what your output is. You can use it for classification or regression problems. And it splits data based on variables. One of the wonderful things about all of these sort of like CART, forest, XGBoost models is because they are nonlinear, it means that you don't have to use the same variables in all the same different places. If you look at a tree, you can have age as your first variable, and then if you're less than 25, maybe it's are you at university, yes or no, as your second variable. But if you're over 25, maybe it's do you work as your next most predictive variable. So when it comes to these types of models, there is a lot of they can fit the data a lot better. That does mean that you run into the risk of overfitting, which means that if you're not careful about how you build these models, you end up with a model that's really strongly fitted to your training data set, and then it doesn't translate well into the real world. But anyway, those are some of the challenges with those. Random forests is an ensemble of decision trees, and basically it takes multiple trees, and then it uses those multiple trees to build your final model. This does mean that accuracy and stability are improved, which is really, really important. And it includes randomization. So effectively, you don't use every single record in your training data set. You have multiple training data sets and validation data sets to build your model, so that it uses 70%, for example, to build the first tree, and a different 70% of your records to build the second tree, and another different 70% of records to build your third tree. And the reason this is so helpful is because it means that you have a far more nuanced set of predictions. And then XGBoost, which is gradient boosting for tree algorithms, it's even more optimized. So here you're using a combination of a subset of your variables and a subset of your records. So for example, maybe day of the week is extremely predictive. With XGBoost models, because you're only choosing, for example, 70% of the variables to use in any given tree that you're building, maybe day of the week doesn't come into a whole bunch of trees that are using, and therefore other variables come higher up the hierarchy of where the value is added and where the prediction lies. The key challenge with CART and or with these models, so random forest and XGBoost, is they're incredibly difficult to work out actually what's going on inside the model. There are techniques that mean you can have a look at it, but it's still quite opaque. So a tree itself is super easy. you can see which variable is the first one, and then which variable, and then which variable, and where those splits are. Similarly, with a linear model, you can see which variables went into the model. You can see the coefficients associated with those models. Therefore, you can work out how strongly predictive each variable is. So if you're trying to be really transparent, so if you want to be able to accurately say what's driving the outcome, those models give you a much better answer. When it comes to forests and XGBoost models, that is far, far, far more difficult to get into. Sorry, Paul, quick question. How much time do I have?
Hi, sorry, I was batting to unmute myself there. We got to 1 o'clock.
Okay, cool. Yeah. Because I don't, I can carry on talking about this stuff for hours, but I'm fairly certain no one wants to listen to me for hours. Cool.
Okay.
Okay. So, sorry, what I was saying about nonlinear algorithms can be very, very, very predictive. But one of the challenges with them is that it's sometimes really difficult to understand what's driving the yes or no decision, what's driving the answer that you're getting. If we look at some of the other nonlinear algorithms, we've got k-means, which is a clustering technique. It's unsupervised machine learning, and it takes a data set and it basically divides it into a number of clusters. And you define how many clusters you want to create. You want to create 2, 5, 22, 7,000. You tell it how many you want. And then what this particular technique does is it finds a center for the cluster. And then it grabs all the data closest to that cluster. And there are various ways you can do it. Typically, we use Euclidean distance, which basically is just a square numbers. And it keeps adding data until it's stable. The trick is that if you've got two centers, a data point might fall into one or the other. And as those centers move around, because they will as your model is being built, so that data point may fall in or out. And what you're wanting to do here is you're wanting to minimize the variance within the cluster. So in other words, all the points that are in the same cluster are as similar to one another as possible. And you want to maximize the variance between the clusters. So cluster A and cluster B and cluster C are very different from each other, as different as they can possibly be. And that's the tension that this particular technique is trying to refine. Right, then we start talking about performance metrics. So one of the things that's really important to understand is, well, how good is my model? Is it working? And for classification problems, we typically use the classification accuracy. So did it say yes when it was supposed to say yes? And did it say no when it was supposed to say no? And that's really what it's trying to do with all of these. You can use things like a Gini coefficient or ROC, and the acronym definition is escaping me at the moment, but the area under the curve, and you can use confusion matrices, and all these things are basically saying the same thing. Did it give me the right answer when it should have, and did it give me the and did I minimize getting the wrong answer? And this is because classification is typically a yes, no, it's a binary thing. I mean, okay, yes, there are some techniques like where you linear discriminant analysis, where you're looking at is it block A, block B, block C, but it's trying to work out that it put it in those right groups. For regression problems, we're primarily looking at how accurate is it. So we use the root mean square error, and we use the R squared. So is the predicted line strongly correlated with what we expected it to be? And how big is that error? So if you remember the straight line through the data, the root mean square error is basically saying, are all those points as close together as they can be? Have we minimized the amount of variance and error in there? And those are the key things for that. And then we get to comparing models. So one of the things that we tend to do when we're building a model, we won't just build one model, we'll build several different models. And then we go, okay, so now which model do I use? And we need to be really consistent in how we do this. So, and consistent doesn't mean the modeling technique. What consistent means is, did we use the same starting data set? Are we comparing apples with apples? What does good look like? So, and good might in one environment mean I just need to know that it's accurate. I don't care how it got to the answer. I just care that it got to the right answer. And in those cases, so typically an example would be, say, fraud. So in application or in transaction fraud, no one really cares whether it's a black box that the answer comes out of. What they care about is if a transaction needs to be stopped because it's fraudulent, is it likely that it actually is fraudulent? What are my false positives looking like? A different example would be, I've declined someone's personal loan. People might really care, well, why did I decline that loan? Is there some sort of bias involved? I think I'm a great risk, and why did you decline my loan? And in those instances, I need to be able to explain what was going on. So all these techniques and all the stuff that we've spoken about to now, the transformation of the variables, the techniques that we use, which variables do we include, which variables don't, if they're closely correlated, why pick one over the other, or why put too many of, if we put so many in that are too closely correlated, what does overfitting look like? All of those are the types of things that come up when we say, well, what does good look like? So when I build models, my first thing is to understand, well, where am I using this model? What is its purpose? What am I trying to do with it? Does it matter that I can explain to someone on the other end who isn't a modeling expert how I got to the answer that I got to? If it is really important that I be able to explain how the model got to the answer that it got to, then I need to do something that is more transparent. So typically it would be some sort of linear type model where I can use variables. That's not to say that you can't build some ensemble. So for example, say you have a lot of variables that are closely correlated. You might want to do something that creates a single variable out of that. So linear discriminant analysis, principal component analysis is another really popular one. What it does is it basically takes these strongly correlated variables and it creates a single variable out of them. And that maximizes the information in that variable. And you know that perhaps the 10 variables that went in there are all related to recency of payment. So have you been making your payments? And then that variable can be used in your final model. And it says, actually, we now understand that all this information that we have about how frequently you've been making payments, how predictive is that in terms of the final score? So yeah, success is a really interesting thing. And I think for anyone who's getting into machine learning and model building, the first thing you need to do is be able to clearly articulate, before you even start gathering data, before you even start with model building, what does good look like at the end of this? What do my users need to know? What am I trying to do? Yeah. And there we go. That is all from me. So I won't stop sharing just yet, but if anyone has any questions, I'm very happy to answer them.
Oh, thank you very much for that, Caroline. Everyone, you're welcome to unmute yourselves. You've got a question or pop in the chat if you're shy, and I'll ask for you. Caroline, I was just wondering, it's kind of for someone like myself who knows, well, I'm going to say that knows nothing about machine learning other than what you've presented today. What is the starting point for me?
I would say data. So getting to understand the data is probably the most crucial thing, because writing the code that will give you, I don't know, a linear regression, that's not particularly difficult. I mean, feel free to grab a copy of my cheat sheet. But it's around being able to understand and interpret the data. So having a really good understanding of whatever domain you're working in. And then I would pick something. So I've done a lot of work in SAS. I now work a lot in Python. SAS, Python, R, NIME, they're all kind of the same envelope. It's what you do with them inside. So if you're wanting to get into it, probably Kaggle, lots of data sets, lots of opportunities to learn there. Lots of really, really knowledgeable people who are extremely generous with their time. And yes, start playing with that. I would say that's probably one way to go.
So you talked about your cheat sheet, and I see you've got the QR code to Python machine learning. How important is it to know Python or to understand, or let me add another question onto that. As a business analyst, would it be important for me to be able to code in Python or to understand or have a knowledge of Python?
I suppose it depends on what you're trying to achieve. So if you're working with someone who is a machine learning expert, I don't think you need to know either Python or how to code in it or know it. I think you need to know what are the right questions. So is it more important? I would have expected that it would be important to understand, well, what is this model trying to do? And how good is it doing that? And when you built the model, how did it perform on training data, and how old was that data? So as soon as we start building predictive models, we have to go and get historical data. And how long ago did we go and get that data? Is that data, 5 years old? And is the world still similar enough that we can leverage it? Or is the data, think pre-COVID, everything's changed. So can we still infer that the results are the same? So I think from a business analyst point of view, it's probably really important to understand the principles. So if someone's thrown in 10 different variables and they're all super similar, it's going, well, what value are they adding? Why have you got all of them in there? And what concerns do you have about overfitting? Because that would be a bigger concern from, I would expect, the business's point of view. Because it's not like everyone can suddenly become a machine learning expert unless that's, what they're wanting to do, in which case, great. But it's around going, okay, so what is the purpose of this model? And is it actually fit for purpose? Are we using too many similar variables? Or has the variable changed? Did we decide to use it for something else in the middle of, I don't know, we just repurposed a variable and now old data doesn't mean what new data means, because that happens.
Okay. Is there any questions from
I can.
Yeah, thanks, Paul. Thanks a lot, Carolyn, for your presentation. I'm just going to ask maybe a couple of very basic novice questions. My apologies if I missed this part of your presentation at the beginning. I just kind of wanted to understand, maybe in the vein of Paul's question around, for a business analyst, where do we draw the line, or where do the transitions happen between, number one, data analysis, and then when does it become data analytics, and then where is the difference when it becomes machine learning and then artificial intelligence? Could you just kind of clear that landscape for me?
Well, I can try and clear up that landscape. It's a great question, and it's probably a little bit murky. So the way I tend to think about it is anything. So if you look at the Gartner kind of review of data, they've got what they call descriptive stats, or what I call basic reporting. It's looking at historical data and telling us what is. That is very typical analytics type work. Then you move into something a bit more diagnostic. So what the hell happened? Something bad happened, and what caused it? What went on? So those sorts of things, depending on how your organizations are set up, might fall within the gambit of a business analyst, or perhaps an analytics team. When we start talking predictive analytics. That's where we start using the likes of AI, machine learning. Machine learning is just a subset of AI, and deep learning is a subset of machine learning. It's all kind of a bit murky. Everyone likes to use the word AI because it makes them feel clever. I don't have massively strong views on that. But as soon as we start talking predictive analytics, at that point, we're probably separating out between what most people call analytics and what other people are talking about in AI or machine learning. So the purpose of predictive analytics is to say, based on this information that I know about a customer or an event or whatever it is right now, I predict something is going to happen at some given point in time. And then beyond that, you get prescriptive analytics, which basically says, knowing what I know now, in order to achieve a certain outcome, I need to do the following things. And again, that I think there's overlap. So I think that there are some business analysts who work quite comfortably in that space. The question starts becoming, does your organization support that? I don't know if that is a particularly helpful answer, but that's where I see the lines falling.
I think that's the best answer I've ever heard in my whole life.
Well, thank you so much.
We please quote you in future.
Yeah, no, there is no one size, unfortunately, or fortunately, it makes things more interesting. There is no one size fits all. Not with modeling, not with how it gets set up, all of those things. They're all different across it.
Yeah, no, I think it's pretty clear. Thank you so much. I really appreciate that. Yeah.
Cool. You're welcome.
Thank you, Samuel. Is there anyone that has a question? I have one, but I'll give someone else opportunity. Feel free.
No questions for me, but just thank you for a very interesting presentation, Carolyn.
Oh, thank you so much.
So for me as a, I'm not even going to call myself a novice machine learning. I'm probably even below that line. But what I'm trying to understand in my mind is what's the use case, or what are the typical kind of use cases I could use machine learning for?
Okay, broadly speaking, I would divide it into two different things. On the one hand, it's, am I trying to predict something? So I might have a whole bunch of data, and I know that the outcome of that thing in some cases was really good, and in some cases was bad. And I want more of the good stuff. So it doesn't matter what field you're in. I mean, I'm in retail credit risk, so we want more people who pay and less people who don't. But it could be in health, where you want more things where the medication gives you a good outcome, or that kind of thing. So when you've got this, what you do is that's where you have supervised machine learning, and you can use any number of different techniques. And I've only covered off a handful of them. There are loads and loads and loads of techniques. And what you're doing is you're saying, knowing what I know at this particular point in time, can I predict what's likely to happen going forward? And the way you do that is you build a model by taking all your independent variables, your target feature variables, and you then have a target and you set up your algorithms to predict that. That's probably the most common use case. In marketing, they often do things like customer segmentation. So you have all these customers who use stuff, and they all use things slightly differently. But how do we know who we should target and with what? And that's where you start talking about things like market basket analysis, things like association, things like clustering, where we're wanting to put people into different groups or customers into different groups so that we can ensure that we target them with the most appropriate messaging or product selections. So those are your two really big use cases for, are we doing predictive type modeling or are we doing clustering type modeling? But really, machine learning can be used in any number of things. It can, if you're trying to understand what the hell went wrong, and you can just set it to run and you can start seeing, are there patterns underneath? Is something breaking that we're not seeing? Is something being overloaded that we're not seeing? So you can use it in all those sorts of different use cases. There's no one particular thing. Images. Are we trying to see whether there's people I know work in biological sciences, and they're trying to identify unique animals. So they need to know, well, looking at this dorsal fin, which shark is that? And not only species, which actual shark is that? So they can include it in that, in their research studies. So there are a number of different use cases. But like I said, typically it's, are we trying to predict something, or are we trying to create groups?
Okay, so I can certainly see that from a business analyst point of view, kind of being able to use that to predict potential problems or even opportunities for your organization. I'm going to give one last chance if there's any questions. Otherwise, I think
yeah, this is Edwin. I have a question.
Go for it, Edwin.
So far you have considered all the models possible, but that can be actually restricted by the performance you want from the model. For instance, in fraud detection, you need to actually have an answer in seconds, and probably seconds is to be too long. So you actually have to actually limit that by the performance you're expected at the end.
So they're two different things too, and I didn't even touch on model ops, which is what you're alluding to. Model ops is a whole massive space. So in fraud is an excellent example. So we have a whole bunch of data and we build models, and then we implement that model. And we need to, as you say, the decision needs to happen instantaneously. Basically, we have microseconds, not even a second. And that's where model ops starts becoming really important. So model building is completely separate to model ops. And we can build a model offline. We can take months to build it if we so desire, making sure our data is all clean. The key thing when it comes to implementing the model is any transformations that happen to the variables when I'm doing my model building have to also happen when I'm now running raw data into my model to get the answer. So if I've binarized a particular variable, I need to ensure that that variable is binarized before I feed it through into the model. And yes, that whole model ops pipeline, really, really important. And there are a number of different ways. So oftentimes, it will be a function of how it will be incorporated in that decisioning system to approve the transaction, yes or no. Does that help?
Yeah, that's how we everything is actually needs to be considered right from the beginning, but you're actually at the end.
Yeah, I'd say model ops does need to be considered right at the beginning, and that's where what does good look like becomes important. But you can do your model building in a separate space to your model operate. I have seen a model, it was quite a while ago, where the model builders didn't do any pre-cleaning, scrubbing, transformations, anything on their data. And they had fields that were massive and character. And they built an XGBoost model, which was wonderfully predictive. But they didn't realize that some of their variables were changing slowly over time. So what happened when they actually implemented their model is A, it took an extraordinary amount of time to run because the model was so massive. And B, because some of these variables were slowly shifting over time, the model started collapsing fairly soon after implementation. So those sorts of things are really also important to factor into your model building, and how frequently you will be rebuilding models and how difficult is it to implement these new models. So if it's as simple as calling an API and you just change the model out in the background, that's quite helpful. But if it, I don't know, is going to take 12 months and $1 million to implement a model, that tends to be a bit more problematic from a model ops point of view.
Yeah, I can imagine. Thanks. Yeah, it's clarifying a lot. Thanks.
Cool.